Right. Ideal gas law. So ideal gas law, as we're going to learn, is another gas law. It uses a lot of aspects of the combined gas law, but it includes a couple new variables that we haven't worked with before. It also does not have like an initial set of conditions and a final set of conditions, whereas before we had like P1, V1, T1, and P2, V2, T2. We just have one set of conditions. In terms of calculations, it's a little bit easier. There are just a couple little tricks that we need to make sure that we are aware of. Right. First thing that we need to know is that in order for something to be considered for the ideal gas law, it needs to be an ideal gas. Ideal gases are defined by how they behave. So they obey all of the gas laws under all conditions. They don't condense into a liquid when cooled, and they show these nice straight lines. Now, there is another video that's going to be posted to my website, which is has Tyler DeWitt talking about what makes something an ideal gas. I want you guys to make sure you have a chance to watch that. It's important information for understanding why ideal gases act the way they do. It also relates a lot to the next unit that we're going to be working on. So it's like 7 or 8 minutes, but watch that one. That's on my website as well before you start working on the worksheet. Okay. So nothing really fits this definition perfectly, but in order for us to be able to use the equation, we go ahead and we think of things as being ideal gases. So we've done lots of stuff with Boyle's law, Charles' law, and the combined gas law. Here's the next one that we're going to know. All right, ideal gas law, PV equals nRT, PivNert. Now, we're going to learn that you can have your pressure be in either kilopascals or atmospheres. You want to make sure that you're converting into either kilopascals or atmospheres. Now, volume always needs to be in liters. Temperature, as we've talked about before, always needs to be in Kelvin. And then N is something that we're introducing that's different here, and that's the number of moles. We're going to talk about how that fits into this equation and why here in just a second. Now, R is an ideal gas constant. It's always the same number. Which R you choose to use, whether it's the 8.31 or the 0.0821, depends on your pressure units. So if your pressure is in kilopascals, then you're going to use the R value of 8.31. If your pressure is in atmospheres, you're going to use the R value of 0.0821. Now, if your pressure is in anything else other than kilopascals or atmospheres, you're going to have to convert. When we did that brain dump as part of that pressure volume thing, I gave you the numbers for millimeters of mercury and torr. And we talked about how 1 atmosphere is equal to 101.3 kilopascals, which is equal to 760 millimeters of mercury. So you would just have to convert. Probably easiest to convert to atmospheres because it's 1 atmosphere for every 760 millimeters of mercury. So you just have to divide the number of millimeters of mercury by 760 to convert that to atmospheres, and then you would use this R value. All right. So how did we? Whoa, sorry. Here we go. My bad. That was like speed forward time there. How did we get this R value? Well, if you have developing this ideal gas law equation, so we knew that PV over T equals a constant, right? The way they come up with this value is they took standard temperature and pressure, temperature 273, pressure 1 atm. It turns out that all gases at standard temperature and pressure occupy the same volume, and it's 22.4 liters. And that is as long as you have 1 mole of a gas. So if I plug these in, pressure times volume, 273 times 1, and, 273 times 22.4, and a temperature of, back up, 1 atmosphere times 22.4 liters over 273 Kelvin times 1 mole. And the reason the moles fit down here is because they have a direct relationship with pressure and volume. That should hopefully make sense. The more gas you have, the greater the pressure and the greater the volume you're going to have. Now, for any gas under any set of conditions, it turns out that when you do this, you get the same value. Now, scientists did it at these conditions, and it turns out that you have the same number all the time, and they called that R the ideal gas constant. So at standard temperature and pressure, you plug these numbers in, and R for atmospheres came out to be this 0.0821. For kilopascals came out to be the 8.31. Again, note, always use liters, Kelvin, and moles, right, so that the units cancel. Pressure is either going to be kilopascals or atmospheres, making sure that you're matching that R value. Okay, here's a couple of sample problems. What I would do at this point is just look at what's given, right? Here's the equation. Here's a list of all the variables. Again, it was 20 degrees Celsius. Noted that got converted. So if I'm solving for n, which actually when you're using the ideal gas law equation is probably the most common thing that you're going to have to solve for, is the number of moles, because that's a tougher one to measure, right? We can't really measure moles. We have to almost always calculate for that based on another measurement. And this is the way you can do that for gases, since you can't really pour a gas onto a balance and do the conversion that way. So if I'm solving for n, R and T move over, right? PV over RT. Everything gets plugged in. We used the 8.31 number because we had 300 kilopascals, and so those will cancel, and you end up with 0.38 moles. Down here, well, I did it again. Sorry. Where'd it go? There it is. Down here, very similar. If it asks for grams, you're still solving for N, and then you just have to multiply by the molar mass here, which is 32, because it's O2. And that gives you the 4.95 grams. So here's just a couple of example problems. You're going to see lots of examples on the worksheet that you're going to be getting and working on that use this equation. So again, watch that other video and then go ahead and do those problems. You get that done in class and you won't have any homework over spring break. Have a great spring break. Bye.